Good afternoon. This is actually the first live in-person conference I've been to since, well, for a couple of years. I think the last one I was at was actually this one in 2019. So it's this feeling like I'm coming full circle. As I'm getting started here, I just want to start with a couple of, well, I have to figure out how this works first. I want to start off with a couple of quick announcements that we're pretty excited about. So just in this last week, D-Wave and NEC jointly announced an agreement where NEC will be a global reseller for Leap in those 38 countries where Leap is available, Leap being our quantum cloud service. And they will be providing professional services both in Japan and in Australia to start off with. I think this will be expanding into the future. It's really exciting for D-Wave because it's going to accelerate adoption of our quantum cloud products worldwide. And I think this is a great thing for NEC. They're happy about it because it really increases their footprint in the quantum application space. Another announcement I just wanted to mention, we've just announced the availability of our Quantum Quick Start program, which is a bundling of a week-long online training about how to program a quantum computer with a month's unlimited access of leap time sort of together. And this matches and sort of made sense based on patterns of usage that we've seen. If you're curious about more details of that, please stop by the D-Wave booth, and the folks there will be happy to give you more details about that. So I got started in quantum computing because I wanted to help build a quantum computer that would solve problems that meant something to people, that people cared about, to be able to make a difference. And I joined D-Wave just over 15 years ago, attracted by a like-minded group of people that were just then turning their attention to developing a quantum computer based on quantum annealing. For the exact reason that we believed at the time that was the most direct path to valuable quantum application. And 15 years on, I'm very happy with that decision. I think that proved to be a good choice for us. There's always a dilemma, though, when you're talking about developing something new that doesn't exist at a certain point in time. Surely the sun rose as brightly 40 years ago when quantum computing was just a vision, a conception, and in the mind of some theoretical physicists. What are these problems that are so valuable that we lived without, tens of years ago, lived without 10 years ago, that are so important to invest all of this effort and these resources to solving? Where are they? But it turns out that they're everywhere. A recent market research by 451 Research market survey, Fortune 2000 companies, found that a third of the respondents had abandoned projects because the compute resources required were too great. About two-fifths of these respondents were actively engaged in a quantum computing program, that is, exploring potential applications related to their business. And about four-fifths of them had a use case in mind that they were looking to start with in the next few years. So yes, the sun is still shining, it's still rising, but these problems are everywhere, and this is apparently now well known. What I want to talk to you about this afternoon is our roadmap and how we're going to go about solving these problems. So just a couple of months ago, we announced Clarity, our roadmap going forward. I'm going to talk to you about so maybe to start off with, we began with quantum annealing, as you know, and today quantum annealing is fairly clearly the most effective way of addressing problems in the optimization space, which is a relatively large, reasonable fraction of the total addressable market of quantum applications. But there's now a growing body of published theoretical work that makes clear that quantum annealing is always going to be more effective than gate model quantum computing for constraint satisfaction problems, optimization problems. And our roadmap going into the future is always going to feature a series of progressively more powerful quantum annealing systems. And I'm going to talk to you about that in a few minutes. But we also know that there are important problems that businesses care about, that are really only addressable with the gate model architecture. And so the other thing we announced a couple months ago is that D-Wave has begun development of a program to build a gate model quantum computer. And I'm going to talk to you about that as well. A very important part of our go-to-market is based on our quantum cloud service, Leap, the first available ever real-time quantum cloud service with both quantum and hybrid solvers available into it. And I'm going to discuss updates to Leap and Ocean, an expansion of those that will enable computation based on the gate model architecture, in addition to continued improvements in hybrid solvers supporting quantum annealing based on quantum annealing technology. But first, I'd like to go back and talk about something we announced just a couple months ago. We're very excited about a performance update, a release of re-release of Advantage, or performance update release of Advantage, our 5,000 qubit processor, first released last year. A couple months ago, we came out with a version powered by improvements in design and also in fabrication materials and processes that resulted in a much higher qubit yield, enabling us to pose and address larger and more complex problems. Increased dynamic range and precision in problem specification, which gives us higher quality solutions. And also faster anneal times are available on this version than on anything previously. Just an example of something that we've seen with this new release. On 3D spin glass problems, we're getting ground state solutions about twice as fast, getting to optimal about twice as fast as with the original, compared to the original release last year. I want to put this in the context of the previous quantum computing systems that we've released to date, and in the context of this, and do so using this graph, this plot that I'm going to explain to you. Each of the 5,000 qubits on the Advantage system is coupled to 15 other qubits. And yet we can pose and deal with problems where a given variable may interact with more than 15 other variables. This by a process called embedding, which among other things allows us to trade off qubits for connectivity, and to allows us to put very complex problems onto the processor. And by the way, there's software that does this for us in Ocean, and this is how I would recommend engaging with this. But I'd like to consider what is the most extreme case of this, and for a problem where every variable it interacts with and is connected to every other variable, represented by a graph computer scientists call a complete graph, or a fully connected graph. And what I'm plotting here on the y-axis and a log scale is the size of the largest complete graph embeddable in a particular generation of processor. And on the x-axis, when was that system released? And when was it actually solving problems for people? So for example, with the D-Wave 1, had about 128 qubits in it, you can embed a complete graph of 16 nodes. For the 2000Q, 64 nodes. For Advantage, released last year, it was 117 nodes. For the performance update, 177 nodes. This last jump brought for entirely by an improvement in qubit yield. For us, this is an under-the-hood sort of QPU level metric that makes it easier to compare processors across different architectures. It's a little bit closer to the problem space. I'll note here that we can pose and address problems using the technology using hybrid solvers with up to 1 million variables. And for most applications, that's the most effective way of using the technology, where the hybrid solver chooses the best way to call the QPU based on the problem posed. But this is helpful for us to visualize the progression of the underlying quantum processor. Coming up next after Advantage will be Advantage 2, enabled by an innovation in qubit design that's going to give us higher interqubit connectivity, also higher qubit energy scale. The 7,000 qubit Advantage chip will be implemented in an entirely new, a new topology, which we've published on recently, and then an entirely new superconducting fabrication stack that's rebuilt from the ground up towards being able to improve qubit coherence, but importantly, lay the stage for future improvements in coherence going forward. After Advantage 2, we can now understand much better a progression continue to focus on improvements in qubit coherence, also enabling then further improvements in connectivity, and then also increases in qubit count to give us a series of successively more powerful quantum annealing processors that will, give better performance on existing quantum applications and open the door to new ones. But I mentioned a moment ago that we'd begun work on a program to develop a gate model quantum computer. And a little bit about why we're interested in doing that, because there's a reasonable part of the quantum application space that's really only addressable with gate model architecture. From a technology development standpoint, we realized that many of the problems and challenges that we faced and overcome in the last 15 years towards developing a truly scaled and scalable quantum technology for quantum annealing positions us well to be able to attack the problem of building a gate model quantum computer. We really honestly believe the only practical, realistic approach to developing a scalable quantum technology in either architecture is with a multi-layer superconducting integrated fab stack, allowing us to harness a lot of the on-chip control circuitry, multiplexing, et cetera, that allows us to get up to a very large number of qubits. We've begun work on this program. Just a brief overview of how we see this going. We've mapped this out as a phased approach. Step one, developing our gate model qubit within the context of an integrated fab stack. Then that may, in fact, entail modifications to that fabrication stack. Step two will be about validating our approach to scalable error correction. So that is multiple physical qubits acting as a logical qubit, but controlled by on-chip control circuitry in a way that we believe is scalable. Phase three will be multiple error-corrected qubits interacting with each other, setting the stage for phase four, which will be about developing task-specific modules. So much like the modern CPUs, a fully functional gate model QPU is going to have architecturally distinct task-specific components. State preparation, logical qubit interactions, data transfer, these are all going to be necessary. And that lays the foundations for the fifth phase, which is integrating these into a full-scale quantum processor. But it's much more than about simply developing the quantum hardware. Our approach has always been, and we're the first to come out with a full real-time quantum cloud service, hybrid solvers to translate away from the physical hardware to make it easier for folks to interact with the system. And then our go-to-market builds on that with professional services to help customers solve problems, and help customers use their expertise, be in the problem space of their domain, but help them use the technology. So we'll also see innovations, and this is our roadmap for Ocean, our open source toolkit, and Leap, the quantum cloud service. First about an expansion to support future computing with a gate model paradigm, which does look quite different from the user standpoint than does quantum annealing. But then also, for example, we just released the CQM solver, constraint quadratic model solver. This is a hybrid solver that uses the quantum annealing backend. This is a step further. It makes it much easier for many customers to be able to specify problems that they care about, many of which have constraints. So it makes that much easier. And this will progress as well. And we see future hybrid solvers, for example, possibly a mixed integer hybrid solver coming out going forward. So this all fits together for us, and the picture is ultimately there'll be one cloud platform with multiple quantum technologies available. You may have a problem if you're a drug company and you need to be doing quantum chemistry and you need to be using a gate model computer to solve this, to help you with your drug discovery problem. But your next step may include protein folding to make it so that you can have an ingestible drug, or you may need help scheduling a complex drug trial, the latter of two which both require annealing or optimization problem. And so all this integrated within a platform where you don't necessarily need to come to the table being an expert in the physics of the various quantum technologies or necessarily knowing which one is the best choice for the problem that you have. For us, it all comes around to, as I was saying at the beginning, being able to build a technology, build a quantum computer that people can solve problems that they care about. And that's why I'm really excited today to be able to introduce you to a new friend who I just met for the first time in person today, Vidyut Naware of PayPal. He's the director of artificial intelligence at PayPal. And I'd like him to come out and join us. So Vidyut? Hey, it's good to see you. Good to see you. So these are comfy chairs.
Yes.
Is there a break after this? Maybe I can stay here. D-Wave and PayPal have been working together for a little bit. And Vidyut, I wonder if you'd be willing to tell us a little bit about what you folks are working on with D-Wave.
Yeah, sure. First of all, thanks for having me over, Mark. And happy to be here. I was actually, just like you, I was at the same site about 2 years ago. I think it was for TensorFlow World Conference. So it's coming back full circle over the past 2 years because of the pandemic. We've all been at home. But anyway, yeah, let's talk a little bit about what PayPal is doing. So first of all, I guess I'm a little bit different from the crowd here. I'm representing more of an application domain, specifically the financial services domain, and further on top of that, PayPal, which is probably one of the most well-recognized brands, in this space. Basically, let me just kind of quickly introduce PayPal. So as probably most of you know, it's one of the largest financial services company. We typically are processing in the range of about $1 trillion of total payment volume these days. We have about 420 million odd customers on the platform. And one of the biggest problems PayPal faces is around fraud, right? Payment fraud. It's one of the most challenging use cases. And that's also a place where we heavily use AI and machine learning today to solve that problem for us. And while I would argue that we are probably one of the best in class in terms of fraud prevention today, but we also look at it as it's a strategically very important area for us. And unlike most other problems, it's an active adversary problem, right? So as you detect fraud, fraudsters will change their behaviors and they will try to game the system. So it's one of those hard domains. And so while we are best in class today, we anticipate that in order to be on that curve where we keep pushing performance while at the same time managing cost, something like quantum computing could really play a very important role in kind of that journey. So with that in mind, we are actually partnering with D-Wave on a very interesting research POC at this point. And one of my colleagues, Nitin Sharma, he'll be presenting a more technical deep dive on our joint work with D-Wave tomorrow. So definitely, for folks who are interested, please join in. It's in a nutshell, what we are trying to do there is in the overall AI ML workflow, there is a step which is referred to as feature engineering. And within that, there is a sub-step called feature selection, which is about how do you pick the smallest subset of features from a larger set of features, which is a classic combinatorial optimization problem, actually almost tailor-made for quantum. And we are trying to see if we can actually leverage quantum annealing, which again, from an overall scale perspective, compared to the universal gate computers, quantum annealing has a little bit of an advantage. And so it's just at that right scale for us in that thousands of qubits range. So that's why that's what we're working with you and your team on. Yeah.
Well, I'm curious about the, presumably 10 or 15 years ago, well, I don't know, but I would assume PayPal wasn't necessarily thinking about quantum computing. And I'm just curious for how did you experience the sort of the progression to realizing that I think it was time to start getting involved with quantum computing? Like what did that look like?
Absolutely, a great question. Actually, our journey, I would say, started about 2.5 years ago. There's a couple of R&D teams at PayPal, the AI R&D team, which I lead, and then there's also an information security and a cryptography team, which is looking at long-term research activities. So together we joined forces and we started thinking about, essentially quantum was starting to show up on our radar in different, through our channels, which we monitor for various trends. And so we started, our journey there. So it was initially more about talking to vendors and trying to get an assessment of kind of what is the technology maturity, what is the scale at which quantum operates. Also, it was a little bit of getting familiar with the terrain and so on. So in parallel with that, we also started use case discovery, right? Like what are the potential business use cases within PayPal that could benefit from quantum, right? So I already alluded to fraud detection as one major use case that emerged, but there were several other use cases as well. Some of them we felt were a bit too complex for existing quantum, but certainly we went through our own use case discovery. And I think at the end of the day, what happened is, we were trying to find that sweet spot of, on the one hand, we want to have something that works with the current scale at which quantum works. On the other hand, we also wanted to balance that with ease of integration into our existing stack. I think that's a big, and again, we are also an applied R&D group, unlike a pure R&D group, which would probably be more focused on, publishing and so on. We are more focused on kind of trying to bring in innovation into the business. So therefore, that ease of integration. And finally, business impact. I think at the end of the day, we need to show some, dollar business impact. And so all of this combined together to eventually around about a year or so ago, we felt things were right. We had that right use case. And then we started engaging with a couple of vendors, and one of them was DF.
Wow, okay. I just think that's fascinating. I know it's something that a lot of us are interested in understanding more. I guess, and your focus area in PayPal is in artificial intelligence. Like, how would you characterize the role of quantum computing within the larger sort of AI machine learning space within PayPal?
Yeah, absolutely. I'm happy to share my perspective. And I think a couple of speakers before me also alluded to this. I think ultimately there are two broad areas that I see quantum is going to be very disruptive in. One of them is optimization. Obviously, a lot of optimization problems which are very hard to solve. There is at least the promise that quantum may be able to, do them with provable speed up. And I would actually classify that into a further bucket, which is provable, but at the same time also have some business impact, right? So there's no point in proving that some algorithm is exponentially better or quadratically better than a certain other algorithm in the classical domain. But if that doesn't translate to something that is meaningful, it's probably not going to be super relevant for us. With that being for optimization, the other obviously is actual machine learning itself, right? So there are several prior literature and art on this now, be it quantum SVM or quantum PCA. There's a lot of algorithms that are out there, which again have been theoretically shown to be better than their classical counterparts. So these are the two broad tracks we're thinking about. Certainly the optimization track seems to be something that is a little bit more mature. There is a little bit more we can do in that space. And we also have interesting problems to solve in that domain. The machine learning part, we are a little bit more circumspect. And if anything, that was further, I guess, reinforced in some of the talks I attended today, that perhaps there needs to be some more progress in the hardware layer and even at the kind of software error correction layer for us to really focus on that. But again, having said all of that, I think as an R&D team, we are super interested in monitoring these activities and these trends and kind of bringing them into PayPal through the POCs at the right time. So yeah,
that's a picture. Well, thanks. Yeah, thanks for sharing that, Vidyut. It looks like we actually have some time for questions. I don't know, should we entertain questions or maybe we should just keep chatting? No, we should. So I don't know if there are any questions. Of course, I'm not going to be able to see. Oh no, maybe I can.
Any questions?
Yep, over there. Okay, please.
PayPal. And okay, now I have to use the indoor voice, the FM DJ voice actually. So very interested in risk and managing risk at PayPal and how you see quantum technologies and in particular even some of that optimization technology in addressing that in a little bit more detail, in other words, on the problem domain there at PayPal.
Yeah, it's a good question, and certainly risk, is front and center at PayPal. As a part of our use case discovery, we had some internal conversations with some business teams around, for example, there's again some prior work on this, specifically, value at risk estimation using amplitude estimation and things like that. And we've had some discussions, but again, we are still trying to find that sweet spot. I think, and as I said, there is a lot of scope for quantum to disrupt many different areas within the business. But at the end of the day, until we see that maturity and we see that POCs are actually resulting in some monetary benefit, it's very hard to kind of bring it in, right? So this is actually the fundamental challenge we're seeing with quantum, and I presume a lot of application domains have similar experience. There's a lot of interest, but we also want to see some actual movement on the ground. So I'm happy to take that conversation offline. Yeah.
I don't know if there are any other questions. Yes, sir.
Are you looking for like 10% advantage or 10x advantage?
Oh, no, certainly not 10x. We don't expect, I mean, it depends on the use case, to be honest. For example, if you look at fraud domain, if we can get 0.5%, we'll be very happy. But, in certain other use cases where, quantum does have, for example, an exponential speed up, or something like that, maybe it is possible. But again, it's very use case specific, right? So that would be my answer to that question.
Okay. Well, I think one more question. Okay. I don't know. Mark, you should take the question. Yeah. I mean,
I'm not a quantum expert. I'm just trying to see how best to leverage quantum. So this is probably better answered by Mark and others.
For my part, I mean, as a little bit as I described, we see a continued progression of for this type of use case, continued progression of progressively more powerful quantum annealing processors, more qubits, more tightly connected, able to embed much larger, more complex problems. In parallel with that, though, is a progression of progressively more powerful hybrid solvers, which will both sort of continue to make progressively greater use of the quantum processor, while at the same time getting closer to the problem space of the customer. So there are innovations and development that are required both in software and hardware. But if the past is any indication, these are just going to continue. And then at each stage, we find that there are more applications that start to look interesting, applications or use cases that seem to be working before actually get better. So I see that as something that will be driven by improvements in technology, both in software, hybrid solvers, and the quantum technology. Okay. All right, well, thanks so much for your time.
Yeah, thank you so much.